Hey everyone, we're going to look at number 17 in section 4.5 on L'Hopital's rule. And they give you this function here. R is a function of x, has a base of 6 minus x. Notice the parentheses, very important here, raised to this exponent 1 divided by x minus 5. So this is an exponential expression. And they talk about which indeterminate form as x approaches 5. So basically what's happening is x approaches 5 to this. Well, clearly, as x approaches 5, the base is approaching what? 6 minus 5, which is obviously 1. What's happening to the exponent? As x gets bigger, x gets closer and closer to 5, the denominator is getting closer and closer to 0. 1 divided by 0, that indeterminate form is going to infinity, right? 1 divided by a number going to 0 is going to go to infinity. So this is the indeterminate form. And basically what's happening here is the base is trying to get the expression to go look like what? 1 to some power. 1 to any power is 1. Okay, so this is trying to go to 1. On the other hand, as we approach 5, say from below, okay, let's just do it this way, from below. So, 4.9, 4.99, and so on. This difference here, even though it's getting closer to 1, is always a little bit more than 1, right? 6 minus 4.9 is 1.1. 6 minus 4.99 is going to be 1.01, and so on. But it's always a bit bigger than 1. And this exponent here is getting bigger and bigger. Well, any number greater than 1 raised to a higher and higher power is going to go to infinity. And so we have a battle that way going, between 1 or infinity. Which is it? Is the expression going to be 1? Is it going to be infinity? It's indeterminate. Could be 1, could be infinity, could be something in between. Okay. On the other hand, notice if we approach 5 from above, 5.1, 5.01, and so on, this difference now is closer to 1, but a little less than 1, like it's 0.9, 0.99, and so on. And a number less than 1 raised to a higher power is actually going to go to 0. It's approaching 0. So you've got a battle between 1 and 0 that way. So it's real complicated. We don't know what's going on here. How in the world are we going to do this? Well, they want you to evaluate this limit using L'Hopital's rule. This is not a L'Hopital rule form. L'Hopital rule form is 0 over 0. Or what? Infinity over infinity. And plus or minus, doesn't matter. These are L'Hopital rule form. That is not it. We cannot use L'Hopital's rule as is, right? What do we have to do? Got to get this exponential expression broken up. The only way we have to do that is with logarithms, and so that's actually what we're going to do. I'm going to let y be the limit that we're looking for. So y will be the limit, the answer we're looking for. And then I'm going to take the natural log of both sides. I take the natural log of y here and the natural log of all this stuff, just stick it in there. Okay. And when we do this, notice the natural log of the limit becomes the limit of the natural log. How do I push the natural log through that limit? Or another way of saying it, how does the limit come inside the natural log? Well, you can only do that for continuous functions. The natural log function is continuous on its domain, and its domain is all real numbers greater than 0. And this expression over here that we're taking the logarithm of, right, for values close to 5, this expression is going to be greater than 0. And so therefore, we're fine. We can push the log through that limit. Okay, so now why do we do that? So remember, we want to break up this exponential form. We're going to be able to do that because remember this property here, the natural log of a, say, to the n power is the same thing as n times the natural log of a. Remember, the logarithm is the exponent. And so if I'm taking a base and raising it to another power, then I multiply the exponents, right? So I'm going to multiply the exponent n times the exponent for the base a, which is what? Natural log of a. And we kind of just think about this n is coming down in front. I mean, that's the mechanics of it, but the reasoning is back when we look at the properties of exponents. Okay, so with this exponent here is going to come down in front, right? And now as x goes to 5, right, this expression is going to 0. Sorry, it's going to infinity. Sorry, x minus 5 is going to 0. 1 divided by 0 is going to infinity. But this expression here, well, 6 minus x is going to 1, and the natural log of 1 is 0. So this is approaching the natural log of 1 or 0. This is indeterminate. Infinity times 0 could be 0, could be infinity, could be something in between. Okay, and again, this is what the limit is approaching. This is not the value. We can't say that this is infinity. That's not a quantity. This is never 0. This is never 0 for any value of x greater than or equal to 5, not equal to 5, right? And we're guaranteed x is not equal to 5 with this limit expression. Okay, but that's what we're getting closer to, right? This is getting closer and closer to 0. This is blowing up. What's happening is this product blowing up. Is the product getting closer to 0, or is it approaching some other value? But we can fix this. This is not in L'Hopital rule form. Remember, L'Hopital rule form is this or this. And so it's real easy because I just divide by the reciprocal of this. The reciprocal of this is just x minus 5, or just, you can almost see, multiply it together. It's exactly the same as this, right? I haven't really changed anything. But now notice that as we approach 5, x minus 5 is going to 0, right? And again, the natural log of 6 minus x is approaching natural log of 1, which is 0. Now that is L'Hopital rule form. So now I can apply L'Hopital's rule to this. So that's the whole goal in this process, right, is to get us to be able to use L'Hopital's rule. Okay. When we get there, now what do? We take the derivative. Well, let's take the derivative of the bottom. What's the derivative of x minus 5 with respect to x? It's just 1, right? Just 1. So I put a little L there, and I would encourage you to do so anytime you use L'Hopital's rule. Put an L over the equal sign. By the way, notice these equal signs. They're usually put between things that are equal. Most of you are doing that on your support, which is good. If you don't, please do so. And of course, every time, what do we have there? The limit sign has to be there every time until we are able to evaluate the limit. The derivative of the top, what's that? Well, that's a chain rule. The natural log of u, inner function, is 6 minus x. So what's the derivative of natural log of u? It's 1 over u times the derivative of the inner function, du dx, or just u prime over u, right? So 1 over u, 1 over 6 minus x, and the derivative of 6 minus x is -1, right? Derivative of 6 is 0, derivative of x is 1, 0 minus 1 is -1. Okay, so there's the derivative. But now I can plug in directly. I can plug in directly 5. In this expression, it's not indeterminate at all, right? If I plug in 5, I just get -1 over 6 minus 5 divided by 1. So it's just that, which 6 minus 5 is 1. -1 divided by 1 is indeed -1. So there's the limit. Okay. Now on the test, you have to show the support. This is what we're looking for, to show the correct support, that you understand how to set this problem up, take the natural logarithm, and of course then evaluating a limit of this form by rewriting it in an equivalent form, which gives you a L'Hopital rule form, applying L'Hopital's rule, and then getting the limit. You can, of course, use your calculator numerically to check this limit and verify that it's approaching -1. And I would do that on the test. I would check and make sure that I didn't make a simple mistake in here. Okay, but you have to show support. You cannot simply use your calculator to guesstimate what the limit is numerically. You can use it as a check. Keep in mind, this is actually not the limit. This is the natural log of the limit, right? The limit was y. This is the natural log of our limit. So the natural log of y is -1. That means what? Y is e, right? The natural log is base e, and natural log of y being -1, that's the exponent. So y is e to the -1 power, or 1 over e. Okay. And so our limit as x approaches 5 of the original expression is 1 over e. Okay, so L'Hopital's rule in these types, and taking the natural log is the way to go with that. Hope this helps with this one, and let me know if you have other questions.